Hi, I'm Anthony Giorio with Fowler High Precision. Today I'm going to show you a little bit about the Trimos height gauges. With this line of Trimos height gauges, we have varying measuring ranges as well as accuracies. We have V3s, V4s, V5s, V6s, V7s, and V9s. Varying with measuring ranges, accuracies, and functionality. Right here we have a V5, a V5 700. It has a 2/10 accuracy over the full range, and it has a 3.2 squareness over the full range. This is going to allow us to measure features such as our IDs, ODs, center lines, heights, widths, depth, slots, ID grooves, groove widths. There's a min, max, and a delta function, so we can tram across high points and low points. We can capture a TIR flatness as well as run out of a round part. If we go ahead and fire our gauge up, it's automatically going to prompt us to reference our gauge. What that wants us to do is bring the probe carriage up past the triangle here. That is our reference position. So as I drive the carriage up, it initiates the gauge and it prompts us to master our probe. It automatically gives us our probe icon. It's telling us we want to master our probe. So when we come down here to master our probe, we're going to engage the probe down and up, and then we'll repeat that process. And if we leave our probe engaged at our final contact, you're going to see we have 0.98425 of an inch. We are using a 25 millimeter master, which is 0.98425 of an inch. And on our second display here, we have 156 thousandths, which is the diameter of the probe that we are using. Effectively, we're using a 4 millimeter probe. When it's taking this measurement, we are actually not only calibrating our probe, but we're also taking into consideration deflection of our probe. So if we have a longer probe, such as our 12-inch extensions, we have probes with a thinner shank, even just a longer straight probe, you're going to see a little bit more deflection the further your probe goes out. But what we're doing is we're calibrating our probe using the same measuring force and the same deflection when we calibrate our probe as we're going to see when we measure our part. And that's how we're going to maintain the accuracy of the gauge. So as we release our contact, that probe icon disappears, and now we're ready to take some measurements. So if I'll bring my demo piece into the display, into the camera here, we'll start to take some measurements. Before we do that though, let's take a look at our carriage. With our carriage, we have a primary carriage, which you'll see me move with this little handle. I typically use this handle for a large displacement of the gauge. Never pick the gauge up by that. We do have a sturdy handle on the base for carrying the gauge around. We also have a secondary carriage. Our secondary carriage is a floating carriage. This is going to allow us to eliminate any operator error. Any user feel from turning the handle and engaging a measurement on the part is going to be eliminated by a floating carriage, because if we engage that carriage at a specific point, we're going to trigger a reading, and it's not going to be influenced by how hard or how fast we turn that handle. So operator A, B, C, and D should all be getting the same measurement. Within this carriage, you'll see there is a little nut. If I lock this little nut down, now my floating carriage becomes a fixed carriage. This is going to allow us to remove our probe, put a test indicator on there, and then we can run up and down our part, reverting our attention to our test indicator and getting perpendicularity and squareness measurements. So it can be utilized just like your height stand and your test indicator. So with all the features that we can measure, the squareness and the capabilities, the versatility of this gauge is far beyond maybe what you had expected. So I will release my secondary carriage as we go to take some measurements. I will direct your attention to the display, as now number 7 is our reference feature. This is how we're going to establish different references. We can establish up to 9 references with this gauge. You might find multiple datums on your part, and we can establish those values. So if I say reference 1, reference 2, reference 3, so forth all the way out to reference 9, we can establish up to 9 references. It's a nice feature to have because you could establish datums A, B, and C to your part, and then you can utilize maybe 4, 5, and 6, reference 4, 5, and 6 as some center to center dimensions, some concentricity measurements, things such as that, which might give you the ability to not lose your 0 positions on your datums while finding other critical measurements on your part. If I come over here and say and direct your attention to this reference key, it is the number 7 key on the keyboard. It's a little box with a question mark. It looks very similar to the datum symbol on a part. The datum symbol on a part is going to be within a box. It's going to have an A in it, a B in it. So typically I say, datums A, datums B, datums C. Those are going to be in direct relation to reference 1, reference 2, reference 3, and so forth. So you'll also note that there is that same box in the top left-hand corner. It's going to have whatever reference you're currently looking at the display. So right now there's a 1 in it. If I say reference 2, there'll be a 2 in it. Reference 3, a 3, and so forth. Again, so whatever it shows in that top corner is the reference you're currently looking at. If I want to establish my reference, I will come down to whatever position I want to establish a reference, say in reference 1, say 0, say in reference 2, say reference 2, 0 it out, say reference 3, engage my probe, 0 it out. Now I've effectively established reference 1, reference 2, and reference 3, relative to datum A, datum B, and datum C. Those are the references, and that's how you will establish it. If I want to use my resolution, I could dial my resolution anywhere from 5 thou, 5 tenths, or 50 millionths resolution. And you simply toggle through those buttons like so. We did our initial calibration in the beginning. If you need to change your probe in the middle of the process of measuring, to measure some small features, to measure some grooves, any of your different probe setups that you need to use once you've initially calibrated your initial probe that you were going to use, you simply hit the number 9 key, prompts you to calibrate your probe. Again, we would come in here, go up and down to calibrate our probe. So this is how you're going to recalibrate a probe, a new probe in the new process with your probe button here in number 9. We also have direct inch and metric conversion, and that is going to allow us to just directly convert from inch to metric. It's great to be able to do that without having to do some conversions on the side. A nice one-touch toggle on the front of the display makes it nice and easy. In the middle of a measurement, before a measurement, after a measurement, at any point you can directly convert your values from inch to metric. The number 5 function is a unique function where we are going to capture the min, max, and the delta, and that is basically going to allow us to capture the lowest point of a feature, the highest point of a feature, or the difference between the highest and the lowest feature. So if I look at my demo piece here, I have a unique wave-shaped feature with a little valley and a little peak. So if I want to calculate the min or the max relative to the bottom of my part, and I want to find the lowest point in that valley and the highest point in that peak, I'm going to engage my probe and sweep through that. So if I trigger the number 5 key, I'm looking at the minimum value. That's going to find the lowest point. If I come in here and engage my probe, you're going to notice that the top button, the top line, is always going to be a live indicator wherever the probe is, high or low, it doesn't matter. The bottom line is going to follow those values until we sweep through the bottom, and it's going to lock on the reversal point for us. It's like if you were using a test indicator and watching the needle sweep, it's going to just do that for us automatically. So if I come in here and engage my probe, and as I sweep through the bottom, you're going to know that my numbers are getting lower, and then once I cross through that low point, my number freezes as my numbers on the higher side continue to grow. So we're locking on the lowest point in that valley. That's giving me a wall thickness relative to the plate of 342 thousandths. In the same sense, if I wanted to know the max, if I hit this number 5 button again, that's going to toggle me to my maximum function. That's going to lock on the highest point. So if we sweep across the high point, I'll come and engage my probe. And again, my numbers will travel up. And as they're growing, we're going to find that peak. And once we cross that peak, my number locks on, and my numbers on the top line start to drop back down. So that top line is giving me the current position wherever the probe travels, and this bottom number is locking on the max. So 371 thousandths is my wall thickness relative to the top of that peak. From there, so that's our min and that's our max. From there, we have a delta where we have the top and the bottom of our display. Our arrows are showing the top and the bottom of the sine wave, and this is telling us we're going to take a delta measurement. It's going to give us the difference between the two. So if I come over here, engage my probe, and sweep anywhere I want to tram my probe, I've just calculated effectively the TIR flatness, like the parallelism of the top of this part, to about 9/10. If you see this top number again is the current position wherever the probe is. If I want to know, while my probe is still engaged, if I want to know the minimum and the maximum value from where we've trammed, I can say, hit this number 5 key again, the minimum value. So our minimum value here, 7.87200. I could say the maximum value, 7.8729. And as you can imagine, as you can see, that's where our 9/10 difference comes from. That's how we've calculated the overall difference. And again, 7.87255 is our current position of the probe physically in that corner. So you would be able to locate, the high points in the high areas and the low points in the low areas by tramming. So it's like giving you a live indicator reading, just digitally doing it. We can also do run out of a round part, and I can show you that like this. In this same delta function, we're able to calculate run out of a round part. If I take my pin on a V-block, you may have a concentricity gauge to turn your part. You may just use a simple V-block like we're doing today. If I come over here, engage my probe, and then I will rotate my part 360 degrees. You see we've calculated the run out of our part. Our pin has a run out to 2/10. So that's how you'll be able to calculate run out of your round part. So that min-max delta function, again, it lets us lock on low points and high points. It captures the difference between the two. So it's a pretty useful feature. If you have different measurements, like from a location to a high point or a low point of a diameter, we can set a 0 to a location and use the maximum mode or use the minimum mode to get us a measurement relative to the min or the max of a diameter. Also to like the min and the min of a diameter, or the max and the max of two diameters. So taking those kinds of measurements is no problem. So moving forward to our next couple features, we have a centerline callout, we have a delta, which is giving us the difference between the last two measurements, and we have just toggling between diameter and centerline mode. So if I show you a couple things here, if I come down, and we have established our 0 off of the plate, we'll come and take a simple height measurement, 471 thousandths, standard easy height measurement. If we go to the high side of this slot, 1.888. From the probe to the plate is our 1.88 measurement. This is where the gauge is defaulting to giving us relative measurements and incremental measurements. This is a great feature of the gauge. This is very functional and very practical to be used in the shop all over the place. So 1.88 is from the probe to the plate. 1.417 is giving us the difference between the last two measurements, giving us an incremental measurement. So my current probe position in relation to my previous probe position, the difference between those two values is 1.417, which is my groove width here. So if we continue along and land on the high side here, 2.36, my relative measurement from the plate, 473 thousandths, my incremental measurement from my last contact to this contact. So 473 thousandths is my thickness, right? If I continued on, 2.95 from the probe to the plate, 590 thousandths is my groove width. So this is a great way to measure your measurements that are relative to your datum position, as well as any of those grooves and the thicknesses and the widths along the way. There's a lot of critical measurements like that on many, many parts, and this is going to make it a lot easier and take a few less steps in the process. Let's go back and replay this one measurement here. Come back to 0, measure this land, and then measure the high side. Again, 1.888, and then 1.416. If we release that contact, and if we want to know the difference, my delta key here is always going to recall the difference between the last two measurements. So if I hit the delta key, that's recalling this difference feature. So we've calculated that slot width. If I hit the number 6 key, a center line call out, this is going to establish a center line for those last two features. So again, I could do those on any two features. If I measure the bottom of this land and then the high side, 2.95 from the probe to the plate, 590 thousandths is automatically calculating the difference between the last two. If I release the contact, my last measurement drops down and I have a live indicator on the top. If I want to recall that slot width, I just ask for it by hitting the delta key, and if I want to know the center line of that slot, I hit the center line button. So that's what those buttons will do. The gauge will default to remembering the last two measurements it took. You can say, give me the center line of the last two measurements I took, or give me the difference between the last two measurements I took. Your center line and your delta key, number 6 and number 3. And now we can measure some diameters, and measuring a diameter is going to be one of the more common things you're going to do with the gauge. So if we put the gauge into diameter mode, we have a diameter and a center line callout, and this is how we're going to measure a diameter. We'll drive into our part. We'll find relatively close to the center. We're going to set ourselves slightly off center, engage the probe, sweep to the bottom, engage the probe in the top, and sweep to the top. The nice thing about this gauge is when I do engage the probe, I don't have to maintain any force or hold down any pressure. The gauge has a constant measuring force, so we're going to sit on that probe. We're going to allow it to maintain that constant force while we sweep our part through the bottom. And then we'll go ahead and replicate that on the top. So we'll drive it up to the top of our diameter, and then we'll sweep through the top. And once we pass that top point, once we find the reversal point in that high point, the gauge will give us our diameter and our center line. And right now, my center line is relative to the plate in reference 1. If you remember, we've established reference 2 and reference 3. So at any point, at any time, with any measurement that we take, I could say reference 2. And now my center line is a negative value, negative 5.216. From the top of my part to the center of my diameter. Or if I say reference 3, negative 2.46 from this location to the center of my diameter. So I'm able to establish these reference positions and always refer back to them and figure out what measurement is relative to what datum. So if I measure any diameter, I can say, is this diameter relative to datum A, or is it relative to datum B, or relative to datum C? So once you've established those datums, they will be there until you reestablish a new zero position under that datum. Right now we're looking at, say we go back to reference 1, we're looking at the diameter and the center line relative to the plate. If we wanted to do a center-to-center dimension on a diameter, I could say reference 4. Now, reference 4 is kind of an arbitrary number because we haven't established anything to that. So it's just whatever the last time a reference was established. So if we want to reestablish a new position here in reference 4, I can say 0. Now I've just established reference 4 as the center line of my diameter. I could then move forward to doing some center-to-center dimensions. So if I come over here and measure this diameter, engage the probe and sweep through the bottom, engage the probe and sweep through the top, I have an ID measurement and I have a center-to-center dimension. That's great. That's a very easy way of getting a center-to-center dimension. I could come down here and do the same over here. Engage the probe, sweep through the bottom, engage the probe, and sweep through the top. I have an ID measurement, 786 thousandths, and a center-to-center dimension, 1.7 and change, from center of my large diameter to center of the smaller bore over here. So effectively what we've done is we have established datum A, datum B, datum C, and now we have a new datum position in our diameter as well. So we've measured 3 bores, we've got all diameters, we've also got center to each location and center to these 2 diameters. So there's dozens of measurements that we've just achieved by establishing our reference positions and measuring 3 diameters. And it's obviously it's up to an operator to determine what is the critical measurement that applies. So is this diameter relative to this datum or that datum? Is this diameter relative to this datum or that datum, or is it relative to the other diameter? And those are easy things to know when you're just looking at a print and you refer to your print and then you just find the critical measurement. From here, the only measurement that we didn't get was the measurement from the 2nd diameter to the 3rd diameter that we measured. And this is something that can be achieved by referring back to the features on our display. The number 3 key, the delta function, is going to give us the difference between the last 2 measurements we took. And if you remember, we landed on the slots and we landed on these grooves and we calculated thickness and slot width by landing on a location and then calculating the difference between the 2. And it works just the same. It'll give us the difference between this location and this location because I measured this diameter, then this diameter, then this diameter. So these were the last 2 measurements we took. If I hit the delta key, it'll give me negative 2.614 from the center of this diameter to the center of that diameter. So that's great. It's another thing that we can grab another value where we don't have to worry about measuring anything twice or going back or re-zeroing. So it's a great feature to have. That delta key is going to always give you the difference between the last 2 measurements you take. Another quick thing to point out would be if I say I want to do a concentricity measurement of one of these diameters, I could say let's go to reference 5. We haven't established anything in reference 5 yet. Let's measure the ID here in reference 5. Sweep the bottom. Sweep the top. I've got a diameter, I've got an ID, and then a center line. Again, reference 5, we haven't established anything, so this is an arbitrary number. We'll go ahead and 0 that. Now that's our new 0 position. Now we can measure the OD. Measuring the IDs and the ODs are just the same. We're going to engage the probe, sweep over the top. We're going to engage the probe and sweep over the bottom. The same way you treat an ID. Slightly off center, sweep over the top. Slightly off center, sweep over the bottom. Again, doesn't matter whether you start on the top or the bottom. It's perfectly acceptable either way. Now you find on the display my OD, which is 984 thousandths, obviously larger than my ID, which was 700 and change. And then my 0 position is negative 6/10. So what that is telling me is that the center line of my OD and my center line of my ID, they're off by 6/10. And that's in this one axis here. If I took my part and I flipped it and I did it in another axis, I could really develop a true concentricity of this gauge, of this part, excuse me. So that's going to be another way to, another feature, some more functions that we can utilize this gauge with. So that covers most of what we have here. Obviously, we don't talk about it, but you've seen me use a lot our large 0 button, and that just sets zeros and establishes zeros. And one thing to note is that with these gauges, we do have multiple measuring positions. Our standard position is what we've been using through this whole process, but we do have a couple other positions where if I invert my probe, I'm picking up my application position 1, and And this is going to allow us to grow our measuring range by about 4 to 5 inches. From there, we can put it in our secondary probe holder, or we can invert it in our secondary probe holder. Inverting in our secondary probe holder is going to give us our maximum application range. On this particular gauge, we have a 40-inch application range, 0 to 28-inch direct measuring range, and a 40-inch application range. If we were to utilize any of these application positions, obviously we can no longer zero off of our plate. So what we have to do is we have to establish a preset value. Establishing a preset value is a very simple process. If I hold down this P button here, it's right in between the 0 button and the diameter button. It has a P on it for preset. If I hold that down, you'll see it'll prompt the gauge with a preset. If we were to say, use this, for demonstration purposes, if we utilize this surface as our preset value, we can just pretend that, say this is a 5-inch gauge block. We could come over here and say 5.00. That's the value that I'm going to preset off of whatever known height you have. Typically, you're going to just use, a set block, but any known height you have will suffice. So 5-inch gauge block, that's perfect. This is our make-believe 5-inch gauge block. So we'll save that by holding down our blue button. Excuse me, I'm going to hit the button. Then we'll come over to our gauge block, engage the probe, just tap our preset button to establish that 5 inches. And now if we run our carriage all the way up through our measuring range, we're no longer at 28 inches, but we're at 32 inches and 32 inches plus. So that's how you're going to establish a preset. If you were utilizing your maximum application position, you could just establish a preset with, say, a 12-inch gauge block. Or maybe, the standard position in the secondary holder, you maybe use an 8-inch gauge block. So whatever gauge block or known height you have, establish a preset value, hold down that button, tell it what value you want to store it at, engage your probe, tap your preset button to engage that value, and now you've expanded your measuring range by however much in whatever position you're holding. This gauge does have an air ride. We can't export the data. It does have an AC adapter. It can run for up to about 20, depending on what style gauge you have. With this particular gauge, with an air cushion, you can run for about 20 to 30 hours of battery life. Obviously, the more you utilize the air, the less battery life you will have. But that is most of what this gauge is going to have to offer for you. And if you have any questions, feel free to contact any Fowler technician or salesperson.